Hello everyone, welcome back to the Atharva Academy. Myself Chinmay Dhadu. Today in this video, we are going to discuss deformation in body. First of all, we are going to understand deformation in different types of body due to axial load. Here, first case is deformation of prismatic bar under axial load. We know that what is prismatic bar, right? Any bar having constant area throughout length is called as prismatic bar. Suppose we have this bar of length L and cross-section area A. Here we fix left surface of this bar and we apply tensile load P on this bar. This P load is axial load, right? So due to this load P, we want to find out deformation in this bar. What is deformation? Deformation is change in dimension of body. Here we are going to find change in length of this body. So how can we find out? Let us see. We know that stress in this body, that is normal stress sigma, is equal to load P divided by cross section area A. And we also know that strain, that is normal strain epsilon, is equal to change in length of this body, that is delta L, divided by original length, that is L. And we also know that sigma, that is normal stress, is equal to Young modulus into normal strain, that is epsilon, right? So if we put this value here, then we will get P by A is equal to Young modulus into epsilon is equal to delta L by L. And from here we can get value of delta L. Delta L will be PL divided by A, right? So here this is the value of change in length, means this is the value of deformation in this body. Here we can write this change in delta L as delta, or we can also write this as delta L. Okay? In our case, value of deformation delta is PL by A. It is very important formula. So you have to remember this formula. In the GATE, question may be asked from this formula. It may give value of load, value of length, value of area and value of Young modulus. And by using that value, you can find out value of deformation in this body, right? In the exam, you have to take units carefully. Basically, you have to take load in Newton, this length in mm, divided by this area in mm square, into this Young modulus, or we can say value of modulus of elasticity in megapascal, or we can also say that it is in Newton per mm square. So if you will use these units here, then you will get this deformation in mm. Okay? And in the question, always take care of units and also check that answer is asked in mm, centimeter or meter. Okay? Next, we are going to discuss deformation of uniformly taper circular bar under axial load. Here you can see the side view of uniformly taper circular bar. The cross section of this bar is circular and diameter of this bar is varying from D1 to D2. Here it is D1 and it is linearly increasing up to D2. I hope that you can understand this figure. Here I am going to draw this body in 3D for your understanding. Here this is the cross section at this point and it is taper like this. Okay, so it is having circular cross section area and diameter is varying from this point to this point. We apply tensile load on this body. So this body is shown here in 2D. Okay. Now to find out value of deformation in this case, we have to take coordinate system. We will take this point as origin and here this direction as x direction and this direction as y direction. Then we are going to take small strip of this body at the distance of x from this origin, and length of this strip is, let's say, dx. First of all, we will find deformation for this small strip and then we will integrate from length 0 to L. Okay? Now what will be the change in length in this strip of length dx? Let's say it is dl. So it will be equal to p into dx divided by ae. Right? We know the equation of delta. Delta is equal to pl by ae. Here load is same, but length will be dx and this area is area at distance of x. So let's say this area is ax. So from here we have to integrate both the side of this body. So finally change in del. So we will get deformation delta is equal to integration of p dx divided by area at distance of x into e. Okay? And here we are going to integrate it from 0 to L. Here this point is 0 and at this point value of x is L. Okay? Now we need to find value of area as a function of x. Right? Because here area is continuously changing from x is equal to 0 to x is equal to L, and it can be found out as a function of x. Now we know the area at distance x is pi by 4 into dx square, and here this dx is diameter at distance of x, means it is this diameter. Okay? So we have to find out value of diameter as a function of x. And how can we find out? We know that diameter is linearly varying from this point to this point, means it is equation of line. And we know the equation of line. Equation of line is y is equal to mx plus c. Right? Here in y direction there is diameter of this body, and in x direction there is length of this body. Right? We know that at x is equal to 0 diameter is d1. So y will be d1 is equal to m at x is equal to 0. So we will get value of c as d1. Right? And we know that diameter is d2 at x is equal to L. Here this whole length of body is L, means from here to here it is L. So we will get y is equal to d2 at x is equal to L. So we will put x is equal to L. Right? And we know the value of c, it is d1. So I will write here d1. So from here what will be the value of m? M will be equal to d2 minus d1 divided by L. Right? So finally I have diameter as a function of x. For that we have to put value of m and c in this case. So we will have y, that is nothing but the diameter at distance of x, is equal to m, that is d2 minus d1 divided by L1. So it will be d2 minus d1 divided by L1 plus here c, that is diameter d1, into x, that is this, plus c, that is diameter d1. So finally we have value of diameter as a function of x. Right? Now for easiness of calculation we will take this term as k. So it will be dx is equal to kx plus d1. Right? So from here we can put value of dx here and we can get value of area. Right? And finally we are going to put this value here. So we will get delta is equal to integration from 0 to L P dx divided by area, that is pi by 4 into dx square, means kx plus d1 square. So it will be kx plus d1 square, right? Now from here we have to integrate it from 0 to L, then we will get value of delta. So if you will integrate it, then you will get delta is equal to 4pl divided by pi d1 into d2 into e, right? This is the simple maths, okay? So here I just derive the equation of deformation for uniformly taper circular bar under axial load. Here you can directly remember this equation. You don't have to remember this derivation, okay? So finally we have value of deformation delta is equal to 4pl divided by pi d1 into d2 into e, right? Now we want to find out mean diameter for this body. And how can we find out? We will consider that this body is cylindrical body like this, having constant diameter dm throughout length, and we will consider deformation of this body is equal to deformation of this body under same axial loading condition like this. So what will be the value of deformation in this case? It will be PL divided by AE, right? So it will be P into L divided by area. Area is pi by 4 dm square into E, correct? Now deformation in both the body should be same, so this both term will be same. So if we will compare this both the term, then we will get dm square is equal to d1 into d2, right? This dm square will be d1 into d2. So finally mean diameter will be root d1 into d2, and it is geometric mean of diameter d1 and d2, right? If question is asked to find out deformation of uniformly tapered circular bar under axial load, then we can find out from this formula also. Here we have to put PL divided by AE, and area will be pi by 4 dm square. Here this diameter is mean diameter of this body, and in that case we have to take this dm as root d1 into d2. So you will get value of deformation, okay? Now here what is the value of stress? We know that value of stress is load divided by area, right? And here area is continuously varying from this point to this point. So value of stress is also going to be changed from this surface to this surface. Here load will be same, so we can say that stress is inversely proportional to the area. Here area is minimum, so we will get maximum stress at this cross section. And what will be the value of maximum stress? It will be load P divided by area at point 1. So it will be P divided by A1, and A1 will be pi by 4 d1 square, right? And at this surface value of diameter is highest, means value of area is highest. And if area is highest, so we will get value of sigma minimum at this surface, and sigma minimum will be P divided by A2, right? And what is A2? A2 is area of this cross section, and it will be pi by 4 d2 square, right? So we can find out value of maximum stress and minimum stress in this body. I hope that it is clear to you how to find out value of deformation and value of stress in this body. You directly have to remember this formula that you already know, and additionally you have to remember this mean diameter, okay? Now we are going to find out value of deformation of taper square bar under axial load. In previous case it was circular bar, and here it is square bar, means side of this bar is same and it is linearly varying from this surface to this surface, right? At this surface, it is having square cross section of side A, and at this surface, it is having square cross section of side B. Here we apply tensile load P on this body. Now directly remember the value of deformation delta as integration from 0 to L into Px divided by Ax into Ex into dx. Here this Px is load at distance of x from origin. This Ax is area at distance of x from the origin, and this Ex is value of Young modulus at distance x from origin. In this case, we are going to take this point as origin, and we will take this direction as y direction and this direction as x direction. This direction is along central axis of this body, right? In this case, load and Young modulus is constant, only area is varying. So we can write this formula as delta is equal to integration from 0 to L P divided by x into E into dx. Here we have to find area, that is Ax, as function of x. For that we have to find value of side of this square bar as a function of x. Let's say side of this taper square bar is Wx at distance x from this origin. And if we find equation of line for the value of side of this body, then we will get A plus k into x, and value of k will be b minus a divided by L, and here this L is length of this body. You can find it out as similar way discussed in previous case. Okay? First of all, you have to take equation of line, that is y is equal to mx plus c, right? And y will be this wx, means side of this square bar at distance x. And in that equation, you have to put two conditions. At x is equal to 0, this wx is a, and at x is equal to L, wx is b. So you will get this equation. Okay? And from here we can get value of area as a function of x. Area as function of x will be wx square, right? So it will be a plus kx square. So now we have ax. So we have to put this here. If you will integrate p divided by ax into e with respect to x from 0 to L, then you will get delta is equal to pl divided by ab into e. And you directly have to remember this formula. This derivation is not important. Okay? Now in this case, we want to find out mean width of this taper square bar. Let's say mean width of this taper square bar is Wm. So we will consider this taper square bar as this type of bar having constant cross section area as a square, and side of this bar is Wm. In this case, if we are going to find out value of deformation under axial load P, then it will be delta is equal to PL by AE. And here what will be the value of area? Area will be mean width square, right? So it will be PL divided by mean width square into E. And we are going to consider value of deformation of both the body equal. So we have to take these two terms as equal. So if you will compare both this term, then you will find that mean width square is equal to A into B. So mean width of this body will be A into B root. And here this mean width is geometric mean of side A and B, right? So if question is asked for the taper square bar under axial load, then we have to find deformation by this formula, and in which you have to put mean width as root A into B, or you can directly use this formula. Okay? Now what will be the value of stress in this body? And as we know that here cross section of this body is varying from this surface to this surface, value of stress will also vary from this surface to this surface. Here it is having minimum cross section area here, so we will get maximum stress at this surface. Maximum stress will be sigma maximum is equal to load divided by minimum area, that is A square. And minimum stress sigma minimum will be load divided by maximum area, that is B square. So this is going to be the value of maximum stress and minimum stress. Okay? Next we are going to find deformation of taper rectangular bar having uniform thickness under axial load. Here this is a bar of length L and cross section of this bar is rectangular. It is having constant thickness, that is T, throughout length, but other dimension is changing from value A to value B. We apply axial load P on this body, and due to that there will be deformation in the body. We can also derive equation of deformation for this case. First of all, we will take this point as origin, this direction as y direction, and this direction as x direction. Then we are going to find width, that is Wx, as a function of x. So it will be A plus kx, and in this case value of k will be b minus a divided by L. And now you have to use same equation, that is delta is equal to integration from 0 to L px divided by ax into ex into dx. Here this load and value of Young modulus is same. So this equation will be integration 0 to L p divided by ax. What will be the ax? Ax will be thickness of this body into width of this body, that is Wx. So it will be Wx into T into this Young modulus E. Now you have to put Wx from here, and then you have to perform integration of this term. Then you will get value of delta. It will be PL divided by mean width into T into E. And here this value of mean width is B minus A divided by ln B divided by A. This mean width is also called as logarithmic mean of side B and A. Okay? This is called as logarithmic mean. So from here you have to remember this formula and this formula. Okay? And here what will be the value of maximum stress and minimum stress? For maximum stress it will be load divided by minimum area, that is area of this cross section A into T. And what is minimum stress? Minimum stress is load divided by maximum area, that is area of this surface. It will be T into B. So here it is B into T. So I hope it is clear to you. Now we are going to discuss deformation of prismatic bar due to self weight. Here you can see that this is a bar which is vertical, and we fix the upper surface of this body. The total length of this bar is L and cross section area of this bar is A. Let's say density of this bar is rho and acceleration due to gravity is g. To find out value of deformation in this body, we are going to use same equation. Delta is equal to integration from 0 to L px divided by ax into ex into dx. In this case, area and Young modulus is constant. Only load will vary according to the different cross section of this body. Let's say we are going to take one strip of length dx at distance of x from this surface. Here we are going to take this direction as x direction. Okay? So at this surface value of x will be 0 and at this surface value of x will be L. Now for this strip, what will be the value of load px? Now understand carefully that value of load at any cross section area of this body will be value of weight of the body below cross section area of that body. Means if we want to find out load P at this strip, then we have to take weight of body below this strip. Means we have to take weight of this body. And what will be the weight of the body? Weight will be m into g, right? And we know that density is equal to m divided by v, that is mass divided by volume. So from here we can put value of m, it will be rho into v. So weight W will be rho v into this g. Now we know that volume is equal to area into length. So finally W weight will be rho into A into L into G, right? Here this length is length of this body, means this weight is total weight of this body. Now if we want to find out value of weight at distance of x, then we have to take Wx is equal to rho A, L is equal to x and this G. So to find out value of load at distance of x from the surface, we have to take this equation in which this length of the body is taken as x, right? I hope that you understand this point, okay? And here this weight will be value of load as function of x, right? So now we are going to put this load P here. So we will get this deformation delta is equal to integration from 0 to L into load Px, that is rho Ax into G, divided by area, that is A, into Young modulus, that is E, into dx. Now here this rho A, G, A and E are constant, so it will be taken out. And from here this area will be cancelled out, right? And here what is the integration of x? That is x square by 2. So finally we will have deformation delta is equal to rho g into L square by 2e. Correct? So you have to remember this formula. It is the value of deformation delta of prismatic bar due to self weight of this bar. And here understand carefully that there is not any term of area in this formula. Here density rho is property of material, g is the acceleration due to gravity, L is the length of this body and E is the Young modulus, that is property of material. So here there is no any term area in the formula of deformation. So we can say that deformation due to self weight of prismatic bar does not depend on cross section area of this body. Now let us rearrange this formula. Let's say we multiply this formula with A and divide it by A. So here we will get rho g L into A, and we know that W is equal to rho A L into G. So finally we will get deformation is equal to rho G L A into L divided by 2E A, right? And it will be equal to WL divided by 2AE. So if weight is given, then you can use directly this formula. Here this is the total weight of body, this is the length of body, this is the area of body, and this is Young modulus. Fine. Now let's say I want to find out value of stress sigma at x distance from this surface. Means we want to find out value of stress at this strip. We know that value of stress is P divided by A, right? Here area is constant but load is varying. So here we will take P as Px. And here we have value of Px, that is rho into A into x into G, right? This is Px. So it will be rho G A x divided by A. And here this area will be cancel out. So we will have sigma x is equal to rho G into x. This is the value of stress at distance of x from this bottom surface. Okay. Now here if we put value of x is equal to 0, then we will get sigma is equal to 0. Means at x is equal to 0, at bottom surface value of stress is 0. And if we put x is equal to L here, then we will get rho G L. And it is the value of maximum stress in this body. And it will be at this surface where x is equal to L, right? So at bottom surface value of stress is 0, that is minimum, and at this surface value of stress is maximum, that is rho into G into L. Fine. Now we are going to discuss deformation of conical bar due to self weight. Here you can see that this is a cone type body. Here the total length of this cone is L and maximum radius at this surface is R. It is having circular cross section and radius of this conical bar is linearly varying from this surface to this point, right? Now to find out value of deformation, we are going to use same equation. Delta is equal to integration from 0 to L Px into dx divided by Ax into Ex. In this case, Young modulus is constant, only load and area is varying. Here we are going to take one strip of length dx at distance of x from this end. And here we are going to take this direction as x direction. So at this point value of x is 0 and at this surface value of x is L. Let's say density of this material is rho and acceleration due to gravity is g. Here we have to find out area as a function of x. Let's say radius of this strip is r, which is at the distance of x from this point. So at this strip value of area, that is Ax, will be pi r square. Now let us keep this area as it is and we find value of Px, that is the value of load at distance of x from this point. And we know that value of load at this strip means at distance of x from this point will be value of weight of the body below this strip, means load at this cross section, or we can say value of load at this strip will be weight of this body. And what is the value of weight? Weight is m into g, and we know that rho is equal to m divided by v. So from here m will be equal to rho into V. So it will be rho into V into G. And here this V is volume of this body which is below this strip. And what is the equation of finding volume of cone? Volume of cone is 1 by 3 pi r square h. And here this height is x. So it will be x. So if we put this volume here, then we will get load Px is equal to 1 by 3 pi r square x into rho into G. So now we have value of area and value of load Px. And we are going to put this area and load here. So we will get deformation delta is equal to integration from 0 to L. Px will be equal to this term. So it will be 1 by 3 pi r square rho G into x divided by Ax, that is pi r square, into E into here dx. Now this pi r square will be cancelled out, and here only x is variable. So we will take these constant terms out. So it will be rho into G divided by 3E into integration 0 to L x with respect to dx. Now we know that integration of x with respect to x will be x square by 2. And if we put this limit 0 to L, then it will be L square by 2. So finally deformation delta will be equal to rho G L square divided by 6E. And this is the value of deformation for conical bar due to self weight. So you have to remember this formula. And here understand that there is no any term of radius or area of this conical bar in the deformation of this body. Means we can say that value of this deformation does not depend on the radius of conical bar. Fine. Now if you will find total weight of this conical bar, then it will be 1 by 3 pi r square. Here it will be capital R, and this x will be total length of this conical bar into rho into G. Now here what is the maximum cross section area? Maximum area, that is area maximum, is pi into capital R square. Right? It is maximum at this surface where x is equal to L. So if you will put pi r square is equal to A maximum here, then W will be equal to A maximum into L rho G divided by 3. So from here what will be L into rho into G? L into rho into G will be 3 into W divided by area maximum. Right? And here you can see that there is rho into G into L. Here this is L square, means we can write it as L into L. So if we put value of L into rho into G here, then you will get delta is equal to W into L divided by 2 into area maximum into E. So if weight is given, then you can use directly this formula. So from here you have to remember these two formula. And what is the value of stress? That is sigma x. This is the value of stress at distance of x from this point at this strip. We know that stress is load divided by area. Here this load will be Px and this area will be Ax. We know the value of Px and Ax. So from here we are going to put value of Px, that is 1 by 3 pi r square x into rho G divided by what is Ax? It is pi r square. So from here this pi r square will be cancelled out, and we will get sigma x is equal to rho G x divided by 3. So this is the value of stress at distance of x from this bottom point. Now if you will put x is equal to 0, then we will get value of stress sigma is equal to 0. Means at this point value of stress will be 0. And if you will put value of x is equal to L, that is value of x at this surface, then value of stress will be rho into g into L divided by 3, and it is the maximum value of stress at this surface. So minimum value of stress is 0 at the bottom point and maximum value of stress is rho g L divided by 3 at this upper surface. I hope that you understand how to find deformation in different types of body under axial load and due to self-weight of body. From this topic of body, you have to remember formula of deformation and stress. That is also given in the notes. From there you can remember the formula. Now today we will stop here and we will continue in the next video. Till then, stay motivated and happy practicing.